I mean, just to start right in here, well, certainly it's a great pleasure to be asked to give this talk. And I hope it wasn't too confusing with the large lecture next door and all the parking and the logistics. What I'll try to cover here is a set of topics. I'll start with some of the various things we're working on as seismologists at the University of Washington. We really have a great time doing seismology in the Pacific Northwest. I'll talk a little bit about the seismic network that we run from the University of Washington for the region. Then I'll go to the M9 project and the related questions you might have about the New Yorker article from a month or two ago that's gotten a fair bit of excitement about earthquakes again. And finally, I'll cover what we're planning to do with earthquake early warning, a new thing we're about halfway into doing, and then conclude. Okay. And just a little bit about my background. Yeah, it's sort of preordained I'd go into science. My family's full of scientists. I had an uncle who taught physics at Princeton. I have, my mother was a geoscientist, so I swore I would never be a geochemist, which I'm not. She made me carry rocks up, Rattlesnake Hill, and the places that as a teenager were very exciting. So I started into physics, but physics was pretty dull, problem set every week, and geology had field trips and Foster's beer. And at the same time, when I was a senior in college, they were claiming to be on the verge of predicting earthquakes. And you may not recognize this, but this is the Palmdale Bulge. It's a place where in California, the seismologists claim the Mojave Desert has risen up about a foot because the rocks are getting all worked up, getting ready for the next big earthquake on the southern San Andreas. And it did wonders for our funding. But it turned out that in their excitement, they'd kind of doubled the density of leveling lines across the desert and forgot to correct properly for the refraction in the atmosphere. So in fact, the desert hadn't risen. It took 10 years and people retiring to really clarify that. But by then I was into seismology, and I'm really glad I was, although we're still struggling to have any kind of useful predictions at all. This is our kind of greatest discovery from the Seismo Lab. One day I was, after an exciting football game, I was watching the YouTube videos over and over again of Marshawn Lynch breaking through the line, and I noticed the fans always seemed to be swaying in the stands. So I quickly looked at the strong motion instruments, which we have all over downtown, and one of them seemed to show the crowd shouting, as well as other plays in the game, and I sent that to Paul Bowden, the network director. He said, yeah, that looks right, and I sent it to Bill Steele, our information officer, who you probably often see on the news announcing earthquakes, and he was the genius who called it the 12th man earthquake, and the beastquake. The Seattle Times made this great graphic of a seismogram in gray here, and they had me annotate, we kind of watched the tape and made up stuff, and and so he hits the line and he breaks into the backfield and he pushes Porter, the cornerback, who falls over helplessly, and he scored. And then we called that the point after. And but this showed up in 2,000 news outlets in the next 2 days. And eventually I figured out that strong motion station was actually across the street. And so it wasn't quite as impressive as I'd thought. But it really did document that the Seahawks Stadium was very loud. So that's probably our most well-known result. But this is another kind of more serious incident, and this is from our Facebook page. The PNSN has very active both Facebook group and page. And one afternoon we were looking at the latest earthquakes, and we saw this blur on the seismograms and spectrograms. I won't explain this in detail. We can see the weird signal near Arlington. And this turned out to be, maybe you can guess, the Oso landslide. And it turned out these are the seismic recordings. This is the high frequency, the kind of rattling that was recorded nearby. And this is the long period, the slow motions. And these turned out to be the constraints that helped the geomorphologists, like the first talk in this series, Dave Montgomery, tell that there was a slide and then another slide hit it, and together the combination made the very liquid slide that went a long distance and did a lot of damage. So very strange looking seismograms, but again, it's very useful to have the seismic recordings. This is an experiment that's currently ongoing. It was actually in the news a few days ago because one of the groups just rushed a paper into print that other groups in our experiment disagree with, so you can read about that. But basically, we're trying to look at the roots of Mount St. Helens. We put about 100 seismometers on top and temporarily put out as many as 5,000, set off 25 explosions. We put electromagnetic sounding around, and we're trying to tell the plumbing under Mount St. Helens and neighboring Mount Adams. We know it pretty well down to the mid-crust, so 10 miles or so down. We're trying to track it all the way down into the mantle, into the subducting slab. And I hope we see something. There's no guarantees. This is kind of new ground. But we'll be reporting on that kind of intermittently, hopefully converging to an understanding the next few years. But again, seismology around the Pacific Northwest is a lot of fun. Another topic I won't talk much about is the mechanics of the subduction zone. So if you've seen the plate tectonics in this region, what's happening here is there's a map on the top, and you can vaguely see the Puget Sound and the coast. And in this cross section, you can see the North American plate, big plate that has most of North America, which is colliding with this Juan de Fuca plate, which is sort of connected by a ridge to the Pacific plate. And this plate's pushing underneath at about an inch or two a year. It moves steadily downward, except it sticks for this part of the boundary about 500 years at a time, and every 500 years it moves about 10 or 20 meters. And so when it does this movement all the way from Vancouver Island down to Northern California, that's a magnitude 9 earthquake. Okay, so that's one of the things we'll be talking about in this hour. But we also look deeper, where there are these slow earthquakes, very strange movements where it takes about a month for it to move, for the stress that's accumulated over a year. So once a year we get a month of motion down there. We call it episodic tremor and slip. It kind of vibrates enough the seismometers can see it, but people can't feel it. And that's steadily loading the lock zone, which is of some interest, but again, too technical for us to talk about here. This was a surprise. Actually, Al Jazeera caught up with me actually in the basement of this building one day to ask me about fracking and tried to trap me into saying the government was corrupt or something. So I made some statements, and they turned out of use to Jon Stewart's show in his last month, which was, again, fun being the regional expert on something and seeing myself be slightly made fun of in national press. But so this is a serious part of the talk. This is the hazard map for America, and the darker colors just means it shakes more often and more strongly. And the clear pattern here is the west coast is red, and there's a secondary dangerous band in the Wasatch Fault Zone a little bit further east. There was a set of big earthquakes in New Madrid 200 years ago, and we're still trying to figure out how dangerous that is for the time being. That's a bullseye. There was an earthquake in Charleston 150 years ago, and we still don't even know what fault that was on, so it gets a red dot as well. But the danger is really here on the west coast. We get regular big earthquakes, and as you're probably aware, south of Cape Mendocino, we're looking at the San Andreas Fault, so it's a sideways moving right lateral strike slip fault. North of Cape Mendocino is the Cascadia subduction zone, which extends to the north end of Vancouver Island. That's our big local earthquake threat. Okay? And we can put estimates on how much this will cost us in the long run. This is technically the annualized long-term expected loss. And this is just the buildings and the people, the immediate damage from the earthquake. And what you can see is California has the biggest danger, $3 billion a year. So as you probably realize, most years there's no damage, and a few years there's tremendous damage. We have about $500 million a year in expected damage. And so again, when we get a big earthquake here, we expect on the order of 100 billion or more in damage, which is about what Japan expected from their earthquake, but they actually lost about 3 times that $300 billion in their magnitude 9 just a couple of years ago. So these are very big impacts in the economy, and fairly serious loss of life as well. But we'll come back to the individual earthquakes here in a minute. The people told me I shouldn't show this plot because you never want to see danger going down, but this is the estimated loss to the buildings in the US, and what you're looking at is the last 20 years, 1996 up to the present. And you know, now the plot I just showed you had about $4.5 billion a year in damage. But in 1996, that was $7 billion a year in damage. And it's a little bit interesting that, you know, it's not that the buildings are that much safer, because we have ever more buildings, as well as the old buildings aren't disappearing that fast. But what's happening here is the seismologists are finding that maybe the motion is less than we expected a few years ago. The motions aren't likely to be quite as strong as we thought. But this doesn't take into account things like the economic impact, which grows over time, and also there's a lot of unexpected things that come up, and the exposure to unexpected things is growing with civilization and the built environment and growing. So this is a little bit misleading. So to come to our favorite plot, you know, this shows again the tectonics. It's similar to the plot I showed a minute ago with the map of the Puget Sound and the plate boundary here between the North American plate and the Juan de Fuca plate that shows the connection with a ridge and transform system to the Pacific plate. And these colored dots indicate the 3 different kinds of earthquakes that cause the damage around here. And it's actually fairly equal, the damage distribution between the 3. So the red indicates the plate boundary events. So you can see, for example, the label that we had a magnitude 9 in the year 1700, 300 years ago. And we'll come back and talk about those more. The pink dots are the ones you probably remember. The Nisqually earthquake in 2001 was one of these. And these are the ones where, as this Juan de Fuca lithosphere, the cold top of the slab is sinking, the slab bends, it kind of crumples in the corner here, like a tablecloth at the corner of a table. It's bending laterally as well as vertically. And there's heavy material, it's cold and sinking, and that's pulling on this slab. Between the crumpling and the pulling, we get earthquakes, okay? So we've had the 3 in the last 100 or so years. And the third kind of earthquake are these yellow dots. They're the ones that are up shallow in the top 10 or 15 kilometers, crustal earthquakes. And these are infrequent, but these are the most feared ones because they would be very strong shaking, localized, and they tend to be very near the cities in the Puget Sound. Okay. So here's the hazard map zoomed into the Pacific Northwest, and you can see a couple of things. One of them is that we carefully map the faults near the cities. And also, well, our cities do have dangerous faults. You can see the worst danger is right on the coast, because that's right above where the megathrust would break. There's also faults in eastern Washington and Oregon, fewer faults, but there is a set of faults right through Hanford Nuclear Reservation. So we have a fairly dense monitoring network there. As you're probably aware, Hanford has radioactive waste and fairly old tanks. And so that's a focus of where we're trying to estimate the risk precisely. This is zooming into the city of Seattle. And again, darker colors is more danger. And this is intended to highlight that one factor in Seattle is the Seattle Basin. So that's kind of this whole darker region. There's higher ground, harder rock to the south and to the north. This basin is here partly because the Seattle Fault runs right through the port of Seattle, just south of downtown, although I'll show a better map in a minute. And then the third factor is the surficial geology. You can see that University Village is on kind of shaky ground here, and the Interlake area is not very solid either. And the big issue is the downtown and the Duwamish. Okay, the downtown is partly hills that have been sluiced off and leveled out, very wet sand that's easy to liquefy. And the Duwamish Valley is filled with a lahar that's come off Mount Rainier volcano about 5,000 years ago. So again, it was after the glaciation. Things from before the glaciation have been pressed pretty thoroughly, and it's fairly consolidated. But these more recent deposits are very wet and soft and will perform poorly when the ground shakes. Okay? So you can see the map of where the trouble spots are around Seattle. Okay, so our seismic network is, our jurisdiction is the states of Oregon and Washington. We have hundreds of instruments, depending how you count, but about 400. Some of them to record the strongest motion, some of them very sensitive, high-quality instruments. There's GPS across our region as well to watch the earthquakes and ground motion. We have ties to the networks in California, the network in Canada, and the national network with stations to the east because we need to surround earthquakes to get a good analysis. We have a collaboration. We work with the University of Oregon to maintain the stations in the south, and we work with the DOE to look at Hanford, and we work with the National Science Foundation, particularly the IRIS Data Center, which is just a few blocks of here north in the University District, which is actually the International Seismic Data Center. Very convenient. We have 3 couples where one works in our seismic lab, one works in their data center. So we know pretty well the inside of what's going on in each place. If you go to the web, you can see the things the network produces. You can look at the seismograms. This is a day, 15 minutes per line, enough lines for 24 hours. This was a volcano on a particularly active day. Volcanoes are really distracting. There's always something, an ice movement or a little earthquake or the wind blowing in the trees or some tremor. At the moment, Newberry volcano is acting up a little bit, perhaps. Almost all these things don't lead to anything, but they're kind of distracting. You can also, after any earthquake, see the Did You Feel It map, which just counts how many people noticed that earthquake and how strong it was felt. This is the Nisqually, which had 10,000 people reporting. And this is what we usually look at when the beeper goes off at 2 in the morning and we're wondering if it's worth looking at this earthquake. If some people noticed it, then we're going to get up and make sure the information's correct on the web. And finally, we have the catalog on the web, and you can log in and see our 40 years of earthquakes and sort through and see what's happened in your town and make boxes and cross sections and timelines. So we have a lot of our information just available for anyone who wants to look through it. When an earthquake happens, we kind of jump into action, and so according to this timeline. So if the earthquake happens, we're just still asleep here until 2 or 3 minutes in when the automatic systems report a magnitude and a location and the beepers go off, both for us and for the emergency managers in the states. And sometimes the press notices it first, and they're the ones that wake us up and tell us that something's about to happen. And then for the next 5 or 10 minutes, we get on our smartphones or our computers and check to make sure that the analysis is done right, improve the automatic analysis, and then post the correct information out to the web for the public. So it's about a 10-minute timeline. That's when you can see it on the maps and the seismograms and all. And then we spend up to weeks talking to the press about what's happened. This is what we're doing now. We're trying to just short-circuit this whole system and detect the earthquakes within 5 or 10 seconds, so when they strike, get the location and magnitude accurately enough to push them out. And the point of early warning is we'd like to tell people that the earthquake has happened fast enough to warn them that shaking is coming and how soon it will be coming to them and how strong it will be. Okay, so that's what we're currently, in fact, my phone here, if it beeps and I run out the door, we have the system running and we're testing it. But it probably won't be ready for the public for a few years, as I'll talk about in a minute. Let's see, so here is where, this is one of our newest tools is called Quick Shake. And in order to go back into the football stadium, and for 2 more years, we had to have a purpose, and the purpose was to develop seismometers that would, a web tool that would report the ground shaking within a second or 2 of when an event happened. So that it's valuable for us to be able to see quickly what's happening, aftershocks or checking an earthquake early early on if we're still developing it. But it also turned out to have a use for the football game, coincidentally. And let's see, this is, again, I'm not sure this is going to work. We were testing this beforehand and it was a little dicey. So this is a picture of our Quick Shake tool in action. You'll see it on this monitor and this monitor. And we're testing it out on some activity at the football stadium. And you see something's happened.
And it's really big. I think
So this is because there's a 10-second delay in the broadcast, but the seismograms come in real time, and so it was a successful test of our new web tool. And yeah, we're hoping to try it again this year, but I think the odds aren't that great that they'll be in the playoffs. but we're hoping. So then now I'll talk about these three different threats kind of in detail. The crustal earthquakes, the deep earthquakes, and the subduction zone earthquakes. And here's a map with the crustal earthquakes in the Puget Sound. And again, you can see we're mapping things carefully near the towns. There are faults other places as well, but I'll just point out the Olympia fault, the Tacoma fault, the Seattle fault, South Whidbey Island fault that goes up the east side of Puget Sound, North Whidbey Island fault, and there's another fault up here that connects Bellingham and Victoria and Vancouver. So you get the idea that these cities are all sitting on top of crustal faults. Okay? And this is a map of the several traces of the Seattle fault. You see it run through Seattle and the Bremerton submarine base and Bellevue and Sammamish. So this is kind of a fearsome fault, but it moves slowly. So it only has earthquakes every 1,000 years, every few thousand years. And if this is a run one of my students, Kate Alstead, did, so if there were a 6.5 on the Seattle fault in the rainy season, this shows where landslides are likely to happen. So basically the steep slopes around the city. And a major point here is that in 900 AD, about 1,000 years ago, there was a magnitude 7.2 earthquake, and it might be bigger than that because we lose sight of it as we go out of the lakes here. And that would be a tragedy if it happened today, because we can see the big waves it made in the Puget Sound, and also it would shake downtown Seattle quite intensely and for a fair while. Okay, so this is a rare kind of earthquake, but if it happened again, it'd be quite a tragedy. And it's similarly possible on the Tacoma Fault or the Olympia Fault or the South Whidbey Island Fault. I'll give some numbers in a minute. It's actually not a huge chance. And there is another example of a crustal fault. This is the 1872 Lake Chelan earthquake. This was one that happened when there were few enough people here that for decades the Canadians were able to blame it on the U.S. and the U.S. could blame it on the Canadians because we just didn't know exactly where it was. But as of last year, it's finally been nailed down. It's right near Lake Chelan, and we can see a scarp in this LiDAR image. It's a fresh scarp. That scarp is just the break in the ground from an earthquake. And in particular, we can see this landslide, which is dated to the year 1872. So we're pretty sure this is the scarp that broke in 1872. But it just really is an illustration that anywhere in Western Oregon and Washington, we could have these kind of crustal earthquakes. This isn't the biggest fault in the region by any means. It could happen anywhere. They're just not very common. The second kind of earthquake, again, these deep earthquakes like Nisqually, happen along the subduction zone as well. And this is a map of every earthquake deeper than 40 kilometers in Oregon and Washington. And what you'll notice immediately is most of them are under the Puget Sound. And again, this is where the slab bends, like the corner of the tablecloth. And also, well, that's all I can say is that's why there could be earthquakes like this under Portland. There have been a few, but they're not very big. Could be under Eugene. But they happen to, and all the big ones, be up here. And those three red dots are these three magnitude 6.5 to 7 events, Nisqually and the two very similar ones before in 1949 and 1965. Okay? So these, it costs several $1 billion. Estimates are $2 to $4 billion to repair the damage after the Nisqually earthquake, and we estimate the odds of recurrence of these is pretty high. And then finally, the big earthquake, the one along much of the coast, magnitude 9 is what it is generated if the whole margin breaks. If part of the margin breaks, we could have a 6s or 7s or 8s. And we're lucky in that this guy, Chris Goldfinger at OSU, has made a profession for the last decade or two out of charting these earthquakes. And what he does is he goes offshore. So again, here's the margin from Canada down to California. And in a number of places, he drills holes and pulls out cores of the sediments. And an example of that is on the right. And I'm a seismologist, so I have to take their word for it. But basically, this line is indicated as the surface on which turbidite flowed. A turbidite is a submarine landslide where the shaking has made the material flow down the canyons, down the hill. You can see the bioturbation. That's where the marine life was stirring up the material before the time of the earthquake. You can see the layer of kind of sand and muck that's been deposited by the turbidite. So he's charted these holes and figured out where he sees signs of these turbidites synchronously or at the same time over the last 10,000 years. So this is actually the longest record of a precise history of earthquakes anywhere in the world. And we still argue about some details, but the main facts are kind of a central part of how we estimate the risk around here. He infers that there have been 20 earthquakes that break the whole of Cascadia. Again, this is kind of a dim map, but that's California and that's Mendocino. I mean, not Mendocino, that's Vancouver Island. So 20 events in 10,000 years is a 500-year interval between events on average. Anywhere between 200 to 800 years is in detail is what he thinks he sees. And in addition, he argues for 20 more events in the south. So basically it's twice as dangerous down here, but the events might be a bit smaller because there's 2 for every 1, and then the plate rate's about the same. So a little less motion in each earthquake. So 250-year repeat time down here in the south, 500-year repeat time in the north is what we're facing with these great earthquakes on the coast. Okay? And this is that same information in detail. So this is 10,000 years. I kind of flipped it around so some things are backwards. But this is the current time. This is 10,000 years ago. This is the present. And every long line is when he thinks he sees one of these great earthquakes that breaks the whole of Cascadia. And these short lines are the parts he thinks broke in the smaller events. And you can see some funny patterns in here, probably artifacts of how the data has been collected. For example, maybe it's harder to see the small events in the distant past than it is recently, so maybe they're even more common than you'd guess from averaging over 10,000 years. But you can see the general pattern. You can see some of these are close together, some of these are far apart, and we can actually do statistics, and that's the basis for our kind of hazard estimation. You might also read in the newspaper the debates about how far we can trust these numbers, but they're the best evidence we have. So this brings us to the New Yorker article, which was tremendous. 98% of this article was exactly right, and it was very well written, a nice narrative, but it had a couple of unfortunate aspects. And one is this juxtaposition of these 2 completely unrelated sentences, which people interpreted as connected. So the first sentence, by the time the shaking had ceased and the tsunami has receded, the region will be unrecognizable. And that's true. Where the tsunami comes in and washes out, it'll be terrible. And that's really a mile or 2 from the coast at the most, because the tsunami goes up maybe 50 meters on the coastline at the highest. And this next sentence, top authority, actually the FEMA chief for the region, says, our operating assumption is that everything west of Interstate 5 will be toast. And people connected these 2 and thought that the tsunami would go to Interstate 5. And we had people calling us, concerned about their children at the University of Washington, and people asking should they move out. And the kind of nadir of this is, this particular one's from Fox News, but I don't want to pick on them. CBS had the same thing. Everything west of I-5 will be gone. Seattle, Tacoma, Olympia, Portland, Salem, 7 million people plus tourists. And, you know, within a few days, things are pretty well corrected, but, you know, this is still lingering in a lot of people's minds. And this is the kind of thing we have trouble taking back out of their minds. And actually, there's another aspect of this that I wanted to address, which is that the article kept talking about overdue earthquakes. And, you know, it's true in the south of Cascadia, the earthquakes come every 250 years. You know, it's been 330 since that earthquake in the year 1700. So it's technically overdue. In the north, we're not overdue because it's a 500-year repeat time and it's been 300 years. But in fact, it doesn't make much difference. When you do the statistics of what you saw in the stick diagram, you know, right now here, it's 150% of the long-term average. It's about 1 chance in 300 per year, as opposed to the long-term average of 1 chance in 500, just because we're past the safest 200 years. And in the south, because it's overdue, it's twice the long-term average. So we're almost at the same level of risk compared to the long-term average, even though they're overdue and we're not. So overdue is not a big marker in the time when risk skyrockets in earthquakes. They're much more irregular than people tend to think. So again, something people need to keep in mind when they're reading things like this. Okay, so here are the actual numbers. So for the subduction zone, you know, as I said, it's a 1 in 300 chance a year right now, and so that means about a 15% chance in 50 years. So given the huge amount of damage it would cause, it's well worth preparing thoroughly, and, you know, things like the early warning system and retrofitting the old buildings and tsunami evacuation towers. But it's not the kind of risk that some people get the impression from reading about in the literature. In southern Cascadia, you can get as high as a 40% chance because they have those smaller events as well as the bigger events, a 40% chance of magnitude 8 or bigger earthquake in the next 50 years. These are the numbers that go into the hazard maps that the USGS produces and FEMA analyzes. So the earthquakes like Nisqually, on the other hand, have an 84% chance of having a 6.5 or bigger in the next 50 years. So that's why, you know, we're tearing down the viaduct and rebuilding the 520 bridge. An earthquake like that could easily take out either of those structures, and this indicates probably more than one of these earthquakes in the next 50 years. And then the crustal earthquakes are more similar to the coastal earthquakes in their risk. So an earthquake bigger than 6.5, somewhere in the Puget Sound, has about a 15% chance in the next 50 years. And on the Seattle Fault itself, about a 5% chance. So that's, you know, those are the odds. And, you know, when they put a tunnel under downtown, you know, you hope that that fault doesn't kind of break the tunnel. But the odds aren't all that high. So here's a closer picture of what you might expect in a magnitude 9 earthquake along the coast. This is a picture you can think of as how the slip is distributed. So remember, in the subduction zone, the plate to the west is being pushed underneath this North American plate. So it's at the surface here. It's at the trench offshore, which marks where the North American plate meets the Juan de Fuca plate. And it dives down. And if you go deep enough on this interface, the material is just flowing steadily. So it's not accumulating stress. So this shows where it's locked. It's heavily locked in the shallow part of the subduction zone, mostly offshore. That's where most of the energy will come from in the magnitude 9. And tapers down to smaller amounts deeper on the fault. And the part that breaks might come almost underneath Puget Sound. We argue about whether this boundary of the closest rupture is near the coast or closer to the Puget Sound. That's one of the scientific things we're trying to figure out. And this map shows roughly the shaking that we expect. So again, the shaking's the worst right on the coast. Very strong, long-lasting shaking. And we're still in the red zone here in Puget Sound. Portland's a little less violent. But there's enough shaking to cause damage to big structures out as far as Hanford, out into central Oregon and Washington, because, you know, there's a lot of energy coming out of a magnitude 9 earthquake. All right, so we have this magnitude 9 project, M9. It's an NSF-funded project, $3 million for 4 years, and it does have engineers and seismologists and social scientists working together. And the gist of this project is we have people computing the expected shaking in a probabilistic way. So we're trying not just to take the worst case scenario, or just a typical scenario, but the range of possibilities, and say how likely are we to get what level of shaking. And we hand that information to the engineers that we have that look at the buildings. We're giving it to the people who compute the tsunamis that come out of these earthquakes, the guys who talk about how the downtown will liquefy, and how the people who look at landslides to figure out all the impacts in a quantitative way. And I should point out that downtown Seattle is known to has liquefied the most times in the last century of any place in the country. Because every time there was one of those Nisqually-like earthquakes, that area, low-lying area near downtown and the harbor is liquefied. So we have an array. One of the things we've done is put an array with a bunch of pore fluid pressures and pressure sensors and seismometers. I try not to say that we're hoping for an earthquake, but if one were to happen, we'd have some of the best scientific data on how liquefaction happens from anywhere in the world. But we're waiting. We're just waiting for that. So we're also working on the early warnings I'll describe, and how to make maps that actually convey information, and how to give that to communities that need to prepare for earthquakes. So it's a very broad effort, and with just $3 million and 16 PIs, what it really is 8 graduate students kind of working between the PIs. So we're able to just touch on a lot of different subjects. It's great that the University of Washington has expertise in such a wide range of topics, so we can do that. And we're trying to figure out how we should be telling planners what they need to know, how inadequate some of the building codes are, and we think we're going to see that for some of the tall buildings and bridges downtown, as well as making the right early warning and giving the emergency managers the information they need to know to be prepared. And there's a lot of basic science in great earthquakes that we still need to figure out. And actually, it turns out the hard part of this, it's easy to make a model of how the ground shakes, and it's hard to test whether it's right. And so a lot of our effort is looking at the earthquake in Japan a few years ago, and another near magnitude 9 earthquake in Chile. They're really the only two that have recordings of any quantity that we can compare. And there's a pair of magnitude 8.3 events also in Japan and in Chile. So we have 4 events that we can see if we're in the right ballpark in our simulations and have confidence we're doing the right thing. And I'll just, this is a technical slide, I have to apologize, but basically this is the Japan earthquake. So here's Japan. This is the area that slid. It's like our subduction zone, but in mirror image. The trench is out here. The slab is dipping to the west under Japan. And in this earthquake, it turns out that as far as the engineers are concerned, it simply consisted of 4 pops, 3 or 4 pops. All the rest of the fault motion was pretty smooth and didn't generate enough strong shaking to damage buildings compared to those 4 pops. In fact, this is the giant patch of slip that made the huge wave. It was like 80 meters of slip, kind of a new world record observed in a big earthquake, and right where it's the shallowest part of the fault near the trench, and that's what pushed the water and made the 40-meter tsunami. But that didn't do any of the damage to the buildings. It was too slow a motion to vibrate the buildings in a damaging way. So we're making, and these are seismograms illustrating this point. So these are seismograms various points along 500 kilometers of the coastline. And what you can see is there's a pop here that you can see on a set of stations, earliest on the one closest. And then there's another pop here, and then a pop here. And that's really most of the energy in the strong motion. So that did the damage. The whole rest of this earthquake, even though the shaking lasts on the order of 3 or 4 minutes, the damage came from these 3, basically magnitude 8 pops. So when we simulate an earthquake in Cascadia, we put kind of a smooth background with most of the slip, but then we add in 4 magnitude 8 pops to reconstruct the impact that we need to have for the engineers. We also then need to make a model. So this has the seismic wave speeds and the densities. That's what we need to do the elastic wave equation to follow the vibrations. So this is a huge grid. When we do these simulations, it runs for a week on the Hanford supercomputer. I think we've done 15 or 20 so far. We promised to do 100. We'll see if that, how long that takes. And the main feature here, you can see sort of the subducting slab. That's what's this yellow thing, the cold, stiff material sinking down in the mantle. But the main feature is this black stuff, and these are the basins around Portland and the Puget Sound. That's the geology that most affects the pattern of shaking. And this is a movie which should work. So this is the 3 minutes of an earthquake that took a week to calculate, squeezed down into 30 seconds so we don't have to watch the waves travel as slowly as they do. So there's the earthquake starting off southern Oregon, very convenient to give us a lot of time to be prepared in Puget Sound if there's early warning. And you can see the crack traveling north. This is basically the energy coming right above where the ground's breaking. But you can also see the waves coming inland. You can see the waves getting bigger as they get to the Puget Sound. And that's from the geological basins around Seattle, Edmond, and Everett Basin and Tacoma Basin. But you can see the biggest motions are along the coast, but these are still significant, and they're powerful at what we call long period. And these, it's a little hard to see these, but this is a map of the basin under Seattle. Here's Bellevue and Seattle and Bremerton. And the point is, the Seattle fault is a thrust fault where the south moves up and the north moves down. And so when the north moves down, it's filling with the soft sediment. And what the soft sediment does is it amplifies the waves as they come through. It's like jello. You kind of jiggle a plate and the jello flops around a lot, and that's exactly what the downtown does when the ground underneath it moves a little bit. And it turns out there's a similar basin near Portland. So it's not really under Portland, it's a Tualatin Basin to the west, which is where Intel and Nike have their factories. So we like people to be well aware of what to expect there as well. So these basins are important, and this is a real example of motion in the Seattle Basin and motion to the west of the Seattle Basin. What you can see is that the motion outside the basin for a small earthquake, it's an impulsive earthquake, there's a small shear wave that comes in. And in the basin, it's 3 or 4 times as big, and the motion lasts much longer. I could go on for a long time why this is the case, but you'll just have to take my word for it. Here's a map of it at 5 seconds period. This is roughly the resonant frequency of the tall buildings in Seattle, of the amplification. And again, it's hard to see these figures, but underneath here is the Puget Sound. This is the Tacoma Basin. This is the Seattle Basin. So what you can see is the amplification is affecting a broad area. It's not just a few little hot spots. And that's what we're trying to map out and quantify, okay, in our M9 project calculations. And this is a somewhat reassuring, somewhat alarming figure. It's the motions that come out of our big simulations. There's 2 different runs in here with the different colored dots, and this is distance from the fault, so 10, 100, and 500, a logarithmic scale. This is the amplitude of the shaking, and units don't matter so much because these curves are what we're expecting. Blue for the hard rock sites and black for the soft sites. You can see most of the sites are somewhat under the curve of what we expect for the hard sites. So the hard sites are, maybe even less of a problem than we thought. But here in the basins, they're 2 to 4 times higher than what we expected for the soft sites. So again, downtown Seattle, we have to test this with our 30 different runs instead of just the first 2. But if you double the motions, the engineers are very displeased. And this shows some of the problems of being certain about this. This is a run from the one I showed, the earthquake starting in the south. Basically, it runs toward the cities, and earthquakes send more energy in the direction the rupture is running. It's sort of like a Doppler shift. The high frequency thing you hear with the higher pitches, the one places where the thing's moving toward it. And this is the earthquake that starts right near the Seattle Basin and runs away from it. So it has the opposite Doppler shift. You can see this is a shorter duration of shaking, but a much larger amplitude. So very different implications for the engineers. But at this point, I should bring up that the engineers generally haven't been designing for 20, 30, 40, 50 cycles of the motion, which is what these magnitude 9 earthquakes do, because they last minutes. So again, we're trying to give the engineers the real motions that they're likely to see. So just the long durational challenge of buildings as well as the higher than expected amplitudes. Okay, so that's, I just have one last topic here, which is the earthquake early warning. And this cartoon illustrates how early warning works. So here's a fault. The fault breaks in an earthquake. If we're lucky, we have seismometers right next to the fault. We have some city that we're trying to warn. And we have three advantages here. So one advantage is that with luck, the sensor is closer to the fault that's breaking than the place we're trying to warn. So it gets the wave first. The second advantage is that the P waves travel, which are only about a fifth as big as the S waves, and they travel twice as fast. So when we see the P waves, we can quantify the magnitude of the earthquake and predict what the S waves are that are about to come. And then the third advantage we have is for some of these faults, like the coastal fault, if we see it start to break somewhere, we can guess how it's going to progress. Like if the Cascadia starts in Cape Mendocino, the best possible case, it's got a long ways to go, several minutes of travel before it can threaten the Puget Sound. So with these three advantages, we can get some advance warning. And you can imagine the best case is 5 minutes of warning if it starts in the far corner of Cascadia. The worst case is it starts right under our feet and we have zero warning. It takes us a second or two to calculate, and if you're right there, the S waves will hit you very fast. So we can't guarantee that we're always going to give a warning. But in general, for an earthquake like Nisqually, 50 kilometers deep under the South Puget Sound, we'd have about 15 seconds here before the S waves hit. So that's how this all works. And here we are. We basically had a workshop within a month of the Japan earthquake because it was such a poster child for why people want earthquake early warning. This is the guy from Berkeley with the 3 microphones, and he wrote a lot of the software. That's a good thing. And us from the Pacific Northwest, the guy from Caltech, the USGS is coordinating this effort, trying to keep us on the same page so we have a West Coast system, not 3 different systems with boundaries, which we actually have at the moment that we're trying to argue about. And then the guy from BART, which is the easiest person to argue for why we need earthquake early warning. And BART is, the Bay Area Mass Transit system. So just a lot of words here, but the point is with early warning, there's a lot of things you can do, and they're generally sort of incremental. So it doesn't prevent the damage. It doesn't, stop all the damage of one kind. It just makes everything a little less damaging. And starting with the traffic, you can turn the traffic lights yellow and then red, and people will slow down and won't be so likely to run into each other or panic or fall off the road or whatever. The trains, not only are they less likely to derail when they're moving slowly, but they're less likely to run into the landslides that are likely to come from the shaking. The airports are a place generally on ground that's likely to liquefy in an earthquake. You don't really want to be taking off or landing during an earthquake or just afterwards. Companies are eager to kind of back off their fragile equipment and sequester their hazardous material. Intel already has a crude early warning system because they'll have a lot of very toxic chemicals that they'd rather not, be cleaning up after the earthquake. Computer companies are actually surprisingly motivated, at least to me, to not have chaos unexpectedly in their networks. You can imagine stock transactions and all the things that they could suspend momentarily with little trouble. That people wouldn't even notice if the computer doesn't do anything for 30 seconds. And then they don't have to try to figure out what happened as their hard drives crash and the communication has trouble. In fact, they have ways you can just shift to another system in another country if they have 10 seconds warning. And finally, people would like to know. A lot of the advantage is if you know where you are, you can get to a safer place. Once the shaking starts, it's very difficult to run or walk or do anything. It's very confusing. So if you have a few seconds, you can find your kid. You can get away from the big windows and bookcases. And that's probably a big part of the benefit as well. And the early warning systems are pretty widespread. They started with Japan. Japan has a very sophisticated system. If you ask me, I can tell you Why it didn't do as well as it could. It did exactly what they told it to in the 2011 earthquake, but they didn't tell it the right thing. And China's building one for $500 million now. We like to tell our Congress people Mongolia has an early warning system. Yeah, so it's time now because of the communications and computers and instruments make it something that's quite straightforward to do. The first paper about early warning was written 100 years ago, but they didn't have the technology at the time. All right, so just as an illustration, if you had 10 seconds, what would you do? Obviously what we'd like is an app that will tell you good advice based on where you are, so you don't have to think of this. But you can get away from the windows in the chimney. You can get away from the things that might topple. You can get away from electrical problems. Just find a safe place. You can find your family. You can send a quick text, although if 10 million people are all trying to text, that might be an issue. And you can turn off the stove. You can slow down your car. And if you have enough time, you can go outside. But you don't want to be going outside when the shaking hits. So that's a little bit of a issue to make sure you do what you should, but not what you shouldn't. So again, Bart's the poster child here. And the BART trains, the first argument is there are 40 of them going 70 miles an hour at any given time. And they cost $30 million. So, if you don't want to wreck them, slowing them down helps. The second advantage is that, what is the second advantage? Oh, after an earthquake, when the highways are likely to be impassable because of overpasses and rubble and prioritized traffic, BART's one of the few ways you can guarantee you can get around. They've spent billions of dollars fortifying BART against earthquakes. So you'd like it to be operational, and if cars are derailed and sideways, it's not very operational. And finally, at rush hour, there's about 1,000 people in each of these 40 trains going 70 miles an hour, and protecting them is somewhat of a priority too. More kind of arguments, that's what we use to motivate it, but there have been several earthquakes with $1 billion of damage, like Loma Prieta and Northridge. And studies show that about half the injuries come from falls and things that could have been avoided if you just looked around. So there's basically, and half the costs are these medical issues. So there's a lot of examples of tens of percent of damage that could be reduced if people just had some warning that it was about to shake. And where we are now in the Pacific Northwest is that we've had a workshop in February where we gave test early warning software to a group. I'll just jump to the next one. These are the people who have it. We picked the organizations that have emergency managers because it's a test system. We'd prefer they didn't call up all their friends whenever the alarm goes off because it's going to have a lot more false alarms than real alarms for a while. We'd like to keep our credibility. But you can see, Alaska, Boeing, Intel, Microsoft, Packer, and then the government people, Seattle, Portland, the public utilities, the light, city light, the state government, federal government, and some scientists. And the one thing that's not up, we said emergency management, but I bring this up just to point out some of the subtleties here. The last we heard, we can't give them the warning because by law, if we give them the warning, they have to do the right thing. And they don't know what the right thing is, so they have to figure out the right thing. And in the meantime, they're the only one on the list who can't get the warning. So that's where we are now. And basically, the federal budget has about a third or so of the funding necessary, a third to half. And so we think that we're going to be ramping up to the necessary funding. We think it'll also take a year or two to make sure everything's hardened enough that it's reliable enough to give away. And in the meantime, we're testing things like that app I have on my phone and these computers in the emergency manager's office. So we're hoping in a few years everybody can have the app on their phone and get the warning whenever an earthquake around the region starts and be better protected. So I just had another couple of points to make. This is just a map of the system that would run the early warning. It's got different colored dots for the GPS and the strong motion and the fancy broadband seismometers. But the main point is it's $16 million a year for the West Coast. So right now we have, depending how you count it, about $6.5 million a year to build up the system. And again, we think it'll be ready in a few years. In the long term, what is important is to get some instruments offshore. As I said, the part that breaks is largely offshore. Also, there's some signs of unrest that have showed up before several of the great earthquakes recently. In Japan, before their magnitude 9, there was some patches that had basically magnitude 7 worth of motion over several days, very highly anomalous activity that they didn't know about because they hadn't put in instruments on the seafloor that brought the data back in the real time yet in 2011. And so their response is this year they're putting in this 150 station array, which costs $500 million to be able to watch the seafloor much more carefully. It's all on a cable. It comes in 6 places. So they now have a very good idea of what their seafloor is doing. Here we put out OBSs, if there are some, and there are some now, but in 2 years they're all going up to Alaska. And so we'll be blind. We have actually a cable out to the ridge, the OOI cable John Delaney's group's put in, but it's basically got 2 seismometers. And the Canadians have another 3 seismometers. So a large part of this zone, whatever happens out there, unless it generates an earthquake big enough we can see from shore, we just won't know what's happening. So we're hoping in the long run to put in a cable like they have in Japan, hopefully from the University of Washington. Okay, and then the final point I wanted to make is just that, you know, when they hired me here, and Paul Bowden, he came from Memphis, I came from UCLA, they promised us an earthquake a year. So, you know, here's the magnitude and the timeline, 25-year timeline, and sure enough, there's 13 events bigger than this arbitrary line, 4.8. And so we showed up and we just started waiting. And you know, we like to say we stopped them, but you know, we know better than that. But we have to kind of keep the public remembering what, you know, what happens in an earthquake zone. And it's getting harder the longer it's been since the last earthquake. And this is just the same thing on a map. So the previous 15 years and the last 10 years, you can see all in Nisqually and many other events under the Puget Sound. You can see one under Portland, right off the coast of Salem, towns in southern Oregon. In the last 10 years, you know, this looks kind of exciting, but it's the most remote corner of Nevada. I'm not sure anyone even feels these earthquakes. So we just have to remember that the earthquakes are going to be coming, despite the quiet we've had for a while. So these are just the main points I wanted to make. You know, again, there are several very different kinds of earthquake threats. Part of the problem is that even when we're considering a single earthquake like the 9, we don't really know the pattern of shaking. It could be any of a range of possibilities. I hope I made the point that it's a great place to be a seismologist. It's really fun, at least when the earthquakes aren't striking. And we strongly think we should build out this early warning system, and hopefully with an offshore component eventually. And I didn't talk so much about the long duration shaking in the basins and also the related problem of Seattle's bad buildings. But Seattle has a lot of unreinforced masonry buildings, as I think you saw on the front page of the Seattle Times just a month or 2 ago. We know they're there, we know they're very fragile, but as opposed to LA and San Francisco, there's not a plan yet for how to get rid of them. So we're hoping in the next few years, the city of Seattle, and we're trying to help, can find a way to ensure that the worst buildings are retrofit or replaced. So that's all I meant to say tonight.